Hello and welcome back to Gaming Like It's 1979. Today we are going through part 5 of the game Turing Complete. Let's see where we left off. We are on the conditions level, and I started to do this and then I decided to take a break and see if I could be more systematic about it. So we are going to get a 3-bit input value, which then is going to emit a 1-bit value that is going to be either on or off depending on if one of these many conditions is true. Never, always. All right. So I'm already worried about how we might make this work, how we might make this fit in this kind of constrained space. It's not hard to do conditional logic, but we don't have a lot of room here. So if we look at what our conditions are, all 3 of these being off is never, right? So that means this one is on. So how can we be systematic about this? Well, one thing we could do is try and use these selector bits. So this was a new device, I believe, that was added in a recent update, or at least after the first time I played it. And the key thing about the selector, you might think it's just a mux, but it's not just a mux. The key thing here is that when the selector bit is off, the output is not just off in the sense of the 0 value. It's literally off. And the corollary of that is that we can have, let me pick a good color for our final bus. We'll do this red color, this pink color. The corollary is that we could just have a 1-bit bus going from top to bottom and plug. If everything plugging into that bus is a selector, as long as only one of them is turned on, then we should be okay. So our first one is never. Only output when, never output at all ever, right? So I think that if we take our input here, our 1 decoded bit, and activate the selector, and then leave this off. Right, so we can see here, there's nothing plugged into the input, and the output is red, which means it is actually sending a signal. And sending the off signal, then that should be fine, right? Of course, that's looks like that's true. No, I think that should be fine. All right, great. Do we even need... We might be able to get rid of this selector completely. I think that if we just... But let's leave it there for now, just to be rigorous about it. Now, correspondingly, there's also this always. So if the 4th input is toggled on, then we are always going to be... You know, I think that we actually don't need the selector in this case, because it's okay to have multiple things that are signaling off to a wire. Which sounds wrong to me, but I think it's true. So I think with this one we can literally do that. Yeah, I'm not seeing a conflict here. We might have to back that out, and if we do, we do. All right, so now that's 2 of our, 8 conditions? In case it's not obvious, my explicit plan here is, in fact, to do the easy ones first. So let's go to just that bit being toggled. That's that one. And this is less than 0. So this one is actually rather easy. Less than 0, as we should all know, means that the first bit, or the highest bit, is turned on. However, I think we can have -0. I think the highest bit turned on, that's the highest bit, right? And everything else off. There's a way to have this be -0. Hold on. I think I can set the UI scale. Oh, there. We can set the number format. What is all bits on? No, maybe not. I thought there was a way in I thought there were 2 ways in 2's complement to represent 0, but I must be misremembering that because I certainly can't make it happen. All right, so let's just assume that. So the thing we could do here is break this out. And then if this bit is on, then we know it is, oh no, yeah, less than 0. Right, that is correct. So we could take a selector, put it right there, because I like the idea of keeping these roughly the same position relative to each other. Wire that in. I think we were using blue for the control lines, right? It goes there. And then literally what I really want is tunnels, the ability to kind of run these things under the board completely, but we're not going to get them. All right. Oh, and look at that. So we do, in fact, need a selector here. Okay, and then I think we said it's the 4th one. 1, 2, 3. No, it's the 5th one. It's going to go there, and then it can go just like that. Use the same bit for each of them. Okay, and then if we make that like so, that seems to work. Great. So that's less than sorted. Well, so what I was going to say is, I was wondering, you know what? No, I was going to say maybe we build like a less than predicate in the component builder, but the chances that we're not going to need these broken out for the other ones seems pretty small. Maybe we'll do that for some of the other ones. All right, and now we've got equals 0. This is one that I might break out. We can do equals 0 by doing what amounts to an 8-way NOR, right? If we NOR every bit individually, then I think we will end up with the right solution there. Is that in fact the same as taking the same value and NORing it together? No, because any value valued to itself will end up being No, because we need to reduce this 8-bit value down into 1 bit, which is either true or false. And I don't think we've made that yet, have we? Bitwise negate, bitwise and, bitwise or, bitwise NAND. Yeah, so I think we're going to have to make our own version of this. Okay, so this time I think I am going to go ahead and make a new component. Let's go do it. We're going to call it an 8-way OR. I'm going to do an 8-way OR rather than a NOR and negate it. Because I think an 8-way OR is kind of more generally useful, and because I could use that to make an 8-way NOR very easily. Component factory. I need to switch schematics. We're going to make a new schematic, 8-way OR. My question is, will this actually save any space? I don't know. Let's find out. Okay, so this has one input, one 8-bit input. Put it right here. Okay, I'm going to try and make this as small as possible. Can I actually put it on top of each other? No. No, I cannot. Okay. And then we're going to use these 3-bit ORs. Not going to bother to change colors for this since this is going to be pretty dense. And then a 2-bit OR for the last 2 gate OR. Oh, look at that, it sticks out a little. Okay, and then we want to OR these 3 together themselves. And then an output. And it's a 1-bit output. That is an 8-way OR, right? And an 8-way NOR would be the same thing, just with a not at the end there. You know, I like that. Let's actually do that. Let's make that right now. Just to save some space. I think I can do that. That changes the name. Okay, get rid of that. Move that there. Pop a knot. Now I'm curious if I can actually make this a little more compact. Yes, it's kind of cheating, but that's okay. All right, so now we have a couple of tools that we could use in our toolkit. All right, so where were we? We were working on less than 0. No? We were not working on less than 0. We were working on equals 0. Okay, so for equals 0, we're going to need another selector as before. And we will go ahead and wire that one up. Wire up the control bit, that is. Okay, and now we need our custom component, which it's not letting me use. Son of a gun. After all that work, it's not actually letting me use a custom component in this level. That stinks, because I rarely have criticisms of this game, but look, Component Factory is right there this is downstream of Component Factory. I should be able to use a custom component. But I can't. Okay, I'm not going to complain about it. We need to do the same thing we just did. But we need to do it with real gates. I don't know how we're going to have the room to do all this now. Boy, this is harsh. Oh well, we've used the Component Factory as a... Choose a different color for this. I guess as a prototyping factory. And who knows, maybe we'll need those gates later, right? Yeah. Okay, and then these go here. And that one goes there, and then we got to plug this into our bus. All right, so now let's go ahead and adjust our inputs for less than 0, no, equals 0. Nope, and I forgot something, equals 0. In order to no, I didn't. In order to equal 0, we want to invert this. Oops. That's if it equals 0. All right, and by the same token, it should be trivial to do not equal 0. So let's figure out which of our inputs is that. Not equal 0. So that's 5. That's this one. So let's get another selector. Put it right there. Wire it onto the bus. Wire up the control bit. And for this one, we just need to take the other bus of the OR gate coming off of the OR gate, which is that one. Conveniently, the one that is already on. Great. So now we've got 1, 2, 3, 4, 5 of our 8 conditions. Maybe I will have space to do this. Let's see. This is kind of an adventure. All right, so let's plug an obvious hole, which is this 0, 1, 2, 3 value. And this one is less than or equal to 0. Well, this one actually should be very easy because we're already doing less than and we're already doing equal to 0. So it should just be the union of those, and we can union things by using an OR. So I'm going to go and I want to make a little more space there. And yes, I'm going to be very fussy and reorganize my wires because I want this to be understandable. I want to be able to read it myself. Okay, so now we need another switch right here. And we need to wire that up to its control line, which is here. Okay, so less than or equal to 0. Which of these is which? Well, this is our less than line. We know we're going to need an OR. Literally, it's in the name, less than or equal to 0. We'll just put that right. That doesn't work. I'll put that right there. I see we are encountering the limits. Okay, so that's wired back up. There's our less than. And our equal to 0 is this purple line right here. See, color coding is important. That goes there. And then the whole thing goes there. I'm going to go ahead and use orange because I think the fact that it represents less than is more important than anything else. Why does that say 4? And if that's the case, did I make a mistake? I think I did. Right, I totally did. Absolutely. This is not equal to 0. I pulled the wrong purple wire. It's the purple wire after the not that is the one we want. Which, by the way, implies that we should be changing the color of that wire. Let's use green. Green is bad for that. I don't care. I'm using it. Okay, that goes there. And this goes right there. All right. So the less than case works. How about the 0 case? That works also. Great. And that is our 6th condition. So again, it's not rocket science. This is, I think, a very overwhelming level, specifically because of the number of conditions and the kind of constrained space you have to work with. But if you just take it a step at a time, it should be manageable. So next, we're doing the 6th input, or rather the 7th input, output, I don't know, 7th bit, control bit, 7th condition, which is greater than or equal to 0. And the final one is greater than 0. You know what? Let's do greater than 0 first, because we know that the greater than or equal to is probably going to involve an or. So let's do greater than first. We'll put it right up here, even though we're using... we're not as space efficient as we could be. I'm not going to worry about it. Not going to worry about it. So greater than 0 is quite literally, we could pull from first principles over here, but we also know we have a wire right here, which is literally less than or equal to 0. So greater than 0 is the inverse of that. Right? Yeah, absolutely. So we can pull this orange wire. Ooh, off by 1. Story of my life. Pull that orange wire into there. We'll change its color because it's different now. Hardly worth it, honestly. I might not have given enough space here. So I am going to actually put this selector down a couple of inches because I think I'm going to want to drag that blue wire out for the next one. That goes here. And then lastly, we need to hook up our... Let's do the right one. Ooh, this is getting a little tight here. I think this is the one where I give up trying to make it fit neatly and just tell the computer, make room for it. Oh, that's going to be actually a little bit, maybe not. Bring that there, bring it there, there. Now I should have room for this last one. In fact, we know the last one's going to go here. So let's... Could I have done this a little better? I think I could have. I'm sorry. I know it's might be boring to watch people rewire stuff, but on the other hand, that might be why you watch this channel. So bring that way. And this one, I think, I'm going to leave the way it is. No, I'm not. Just bring it down by one level there, because that will let me do this. Right? Great. And then this one, I think I don't care if it's not neat. Okay. Yeah. Yes, I do. Who am I kidding? I want to have that nice little Tron looking bus for just for a little bit. I think I screwed something up. I've managed to confuse myself. Because that should not be... that needs to be a knot. I grabbed the wrong one. There we go. Okay. And now our very last... Well, let me test the 0 case here. Greater than 0. Correct. So when it's 0, it is not on. That's fine. Okay, so now our very last one is greater than or equal to 0. Okay, we've already got our control bits wired up. Well, is that the inverse of anything? Yes, greater than or equal to 0 is the inverse of less than or equal to 0. So let's grab a NOT gate. Let's do the same thing. Well, I'm going to have to make some room for it. Oh well. Which of these is less than or equal to? I cannot remember. Or is less than 0. Is input 2, which is this green wire here. Okay, let's pull the green wire. We'll pull it. No, it is. Is it? No, I'm off by one. Once again, it's this orange wire. Oh, that's actually perfect, because I can just go right there. And we'll make it, what color did I use there? Blue. Right there. Okay, so less than 0. No, we want it to be greater than or equal to 0. The 0 case has it lit. A greater than case has it lit. And a less than case does not. All right, so I think this is our conditional logic. I'm going to be a little type A here, just for the silly reason of density, which doesn't really matter, but I'm going to do it anyway. And let's move this guy down here. Totally wrong. Wire that back up. All right, let's see if it works. Fingers crossed. My circuit has been saved to the component factory. Well, now I want to go look at the component factory and see, like, what is the shape of that circuit? How did I do in terms of density? Cond. Ooh, that's kind of weird, but okay, I'll take it. I could always go back and try to make it prettier later. Well, we have really been slouching towards Bethlehem here. The only major piece of CPU architecture we have left to do is the working computer. So that feels pretty ambitious, and the conditional chip took me longer than I thought it would because I was being so methodical. So I'm going to cut the video here, and when we return, we will tackle Turing Complete's working computer level. This has been Gaming Like It's 1979. Thanks for watching.